Hello, dear students. Today we are going to speak about predicting the geometrical structure of a molecule. We are going to study the VS-EPR theory. This theory predicts the molecular geometry based on the repulsion among the pair of electrons on a central atom. And also we are going to see the Lewis structure. Let's begin by the last one. Lewis structure. The shape of a molecule is determined by the location of the nuclei and its electron. The electrons and the nucleus settle into positions that minimize the repulsions and maximize the attraction. Let's begin talking a little more in English. Until this moment, maybe you don't understand. Well, what is the Lewis diagram? The dots around the different atoms represent electrons, and they are placed around the element symbol at the points of the compass, north, east, south, and west. Electron dots are placed slightly first until the fifth electron that is reached, and then they are paired. For example, hydrogen has only one valence electron. That is the electron that is in the outermost shell. Then we put only one dot. Helium has two. In the case of helium, we pair the two electrons because helium doesn't have more than one shell to locate the electrons. But look at this in the second row, in the second period, we begin by lithium. Lithium has only one valence electron. Then we represent as a dot. Beryllium has two, then I represent the two electrons, and so on with the rest of the elements. Look at this, lithium 1, beryllium 2, boron 3, carbon 4. Well, until this moment, I represent one dot each side of the element. But what happens when we have more than 5 valence electrons? Well, in this case, look at this. Nitrogen has 5 valence electrons. Then I begin sharing, well, I begin pairing the electrons. And oxygen has 7, then, 6. Then I pair two groups of electrons. The same thing with fluorine that has 7, and neon that has 8. Look at neon. Neon is a noble gas. Why we call noble gas to these elements in group 8? 8, 8. Well, because they have A electrons, valence electrons in the outermost shell, and they have an stable configuration. So they don't need more electrons to be stable. That's why they don't react, they don't react with other atoms. And they are called noble gases. They are inert. Let's go to the following. Well, as I told you at the beginning, hydrogen and helium are in period 1. They have only one shell. Suppose this is the nucleus, and they have only one shell to get or to put the electron. So in this shell, that is correspond to lever number 1, there are only two possible electrons that are in orbital s. So helium has two electrons and is in group 8a. So it's also a noble gas or has a stable configuration because helium has the maximum number of electrons in the outermost shell. Let's continue. Here we have the representation for all the representative elements. As you can see, the dots represent the valence electrons or electrons in the outermost shell. Let's go to the following slide. Now I'm going to explain the water molecule using the Lewis structure. I begin, well, hydrogen has only one valence electron, but I have two hydrogen, then I have two electrons. And oxygen has 6. Then we have at all 8 valence electrons. I have to represent these electrons in the water molecule. Well, hydrogen, there are 2 atoms of hydrogen, 1 and 2, and only 1 oxygen. So we choose oxygen as central atom. And then what I do, I put 2 electrons between hydrogen and oxygen. As I told you before, hydrogen is in level in the period 1. So the maximum number of electrons that hydrogen admit is 2 and make what we call a duplet. But oxygen now has 4 electrons, 2 here and 2 here. Remember that they are sharing electrons. So oxygen until this moment has 4 electrons, but I told you that we have at all 8 valence electrons. Then what we do? We put 2 electrons here and 2 more electrons here. They are lone pairs because they are not shared with hydrogen. They belong only to oxygen. That is, in this case, the central atom. Now we can see that I have represented the 8 valence electrons, and now I'm going to see that hydrogen has a duplet. This hydrogen has also a duplet. So both atoms are satisfied. And oxygen has an octet, 8 valence electrons. That is the maximum number of electrons that any atom can admit. So oxygen is also satisfied. And we can represent these electrons that are being shared by this line. This line represents 2 electrons shared by these 2 atoms. And as you can see, we have in oxygen 2 lone pair electrons. This is the stable Lewis structure for water. Let's go to this compound. This compound has 1 chlorine, 3 hydrogen, and 1 carbon. Methyl, this is a chloride of methyl. well, you're going to study this compound in organic chemistry. Then what we see that we have 3 electrons from hydrogen, 4 electrons for carbon, and 7 electrons from chlorine. At all, we have 14 valence electrons. And the first step is to represent the central atom. In this case, the central atom is carbon. And we have 1 hydrogen, another hydrogen, and another hydrogen, and we put 2 electrons between carbon and every hydrogen. And the same thing between carbon and the other chlorine. Well, if we see hydrogen has a duplet, then it's satisfied. And carbon has an octet, as you can see here. But we need to complete the 14 electrons. How many electrons we have until this moment? 8. Then we have to add 6 more electrons. Then 1 pair here, 1 pair here, and 1 pair here. And now we have 14 valence electrons represented in the molecule. Carbon has the octet rule. Hydrogen has the duplet rule. And chlorine also have the octet. So every atom is satisfied, and we can represent the stable Lewis structure as this one. Let's go to oxygen. Well, oxygen is made of 2 atoms of oxygen. We put the 2 atoms of oxygen, we put 2 electrons in between, but remember that oxygen has 6 valence electrons. Then, as we have 2 oxygen, we have 12 valence electrons at all. Then we have to complete 1, 2, 3, 4, 5, 6 electrons, and 2, 8. But we have 12. Then we have to add 2 more, and we add 2 electrons here and 2 electrons here. What happened with this structure? Well, this oxygen has the octet, but this oxygen has not the octet, has only 6 electrons. How many electrons this oxygen needs to get the octet? Well, 2 more. What we can do? Well, we can share these 2 electrons from this oxygen with this oxygen. How? Well, making a double bond. And now we have satisfied all the atoms. 1, 2, 3, 4, 5, 6, 7, 8. And the same thing here. 1, 2, 3, 4, 5, 6, 7, 8. So now every atom is satisfied, and this is a structure. What we have here? A double bond. In this case, we made a double bond to satisfy the octet for every atom. It is very important to satisfy the octet or the duplet in the case of hydrogen. Let's continue. Let's go now to the BS-EPR theory. Well, this theory predicts the molecular geometry based on what? On the repulsion among the pairs of electrons on the central atom. Let's go to this molecule. For example, ammonia, NH3. What we do? Well, we put the nitrogen in between. We have 3 hydrogen, We put 2 electrons between the atoms. Now we have 1, 2, 3, 4, 5, 6 electrons. But what happened? Nitrogen, as you could see before, look, nitrogen has 1, 2, 3, 4, 5 electrons, and 3 hydrogen is 8. So in this molecule, we have 8 valence electrons. How more electrons we have? Oh, we have 2 more electrons to represent. Where do we represent the electrons? Here, in order to get the octet for nitrogen and the duplet for every hydrogen, as we have done by the Lewis representation. What happened now that this atom has a lone pair? What is the meaning of a lone pair? They are non-bonding electrons. Now, what happened that these electrons will repel the hydrogens, and that's why the molecule will have a specific structure that I will show you in a few minutes. Look at this. Here we have 4 atoms. Or lone pairs, or a combination of 2 with a bonding to a central atom. Look at this. Here we have 4 groups of electrons. Look, 1 group, 2, 3, 4 groups of electrons. 4 groups of electrons. And in this case, we don't have lone pairs. Then, when we have 4 groups of electrons around the central atom and no lone pair, we say that the structure is tetrahedral. Tetrahedral, and you can see here the form of the molecule. But what happens when we have 4 groups of electrons, but only 3 atoms and 1 lone pair? These lone pair are the 2 electrons that belong only to the central atom. Well, in this case, the structure is trigonal pyramid. And it's the case that we have seen before. In the case of ammonia, we have the nitrogen. We have this way a hydrogen, this way a hydrogen, and this way a hydrogen. And in the upper part, we have a pair of non-chair or lone pair electrons, non-pair electron. This is, as I told you before, is a trigonal pyramid structure. But what happens if we have 2 lone pairs? Well, in this case, we have a bent or angular. That is the case of water. We have hydrogen, 1 lone pair, 1 lone pair, 1 hydrogen, and 1 hydrogen. The molecule, as you can see, is bent. And this structure is very important to understand the properties of water. Well, in the last case, we have 2 atoms, but 4 groups of electrons. 4 groups of electrons and only 2 atoms. These 3 lone pairs belong to this atom. And this atom doesn't have lone pairs. then in this case is a linear molecule. For example, it can happen in this element, in this compound, cyanide. Well, let's continue. Then you can see here that when we have 4 groups of electrons, and according with the lone pair groups, we have different structure. You can use this picture. This table is in your book too, in order to do the exercises. All what you have to do is to calculate the number of groups of electrons around the central atom and the lone pairs. And according with this, you can choose the structure of the molecule. Here you have the example for CH4. It has 4 groups of electrons, and all the electrons are shared, no lone pair, so it's tetrahedral. In the case of ammonia, as I told you, it's trigonal pyramidal because it has a lone pair. And water has 2 lone pairs, so it's bent. 2 shared and 2 lone pairs, so it's bent. Here you have the complete table. You can use this table or the one in your book in order to do the exercises according with look in this case, we have 2 groups of electrons, 3 groups of electrons, 4 groups of electrons, 5 and 6. According with this and with the lone pairs, you have different structures. All right? Well, here you have the case of ammonia that I showed you before. Ammonia has an angle of bond of 107 degrees. Is trigonal pyramidal, as you can see here. This is the Lewis structure, and this is the structure represented by this theory. And here we have water. Water have an angle of a bond angle of 104.5 degrees. And because of this structure, you can see that water has more negative charges to this place and more positive charges to this place. That's why we have a dipole moment between the atoms of hydrogen and oxygen. And that's why water is a polar substance. Well, here you have a video. You can click on this, or in this case, well, as it is a video, you can copy and paste and get this video and watch it. I hope that you understood a little bit more what I'm talking about. See you later.